Hello, in this episode, we'll talk about what is reinforcement learning. So reinforcement learning is an agent-oriented learning, which means that it's interacting with an environment to achieve a goal. And I think the easiest example is like training a dog, that you are the programmer and writing a program, and the program tries to learn, isn't it? Like a dog, isn't it? And how does it learn? The main idea is learning trial and error, with delayed evaluable feedback. Okay? And in the dog analogy again, which is that, if you try to teach the dog a trick like raising the paw, initially it doesn't understand, but accidentally if it raises the paw, it gives a treat. It keeps doing that, and after a while, the dog will learn that raising the paw gets a treat, isn't it? So, and that's how they learn. So it's like a trial. Initially, it doesn't work well, but then again and again, and then it does work. In analogy, if you remember the movie Groundhog Day by Bill Murray, he lives the same Groundhog Day over and over again. And initially, he didn't play piano and didn't do much well. But as he lives that same day over and over again, he gets better at doing things and make better decisions, isn't it? And this is the main principle of reinforcement learning. They keep repeating the same situation over and over again and improve itself. Okay? And it is not a supervised learning. It doesn't have a target, the teacher. It only gets a reward signal. And the feedback is delayed. It may not be instantaneous. Like if you think about electronic games like Pac-Man and such, it gets a reward, it gets score, but sometimes you have to move a couple of steps to actually make the move pay off, isn't it? And I guess game is a natural place where to explain the reinforcement learning. So there's a value function. It's kind of how valuable each actions are in a particular situation. So if you think about here like Space Invader, the reinforcement learning consists of a computer program and an action like moving a joystick, left, right, or something. And there's an environment that you play against. So there's a computer program that tries to learn how to play the game. And here's a Nintendo cartridge. And what it does is that your program sees a state, like a situation, what kind of screen you're seeing. And then based on that, it makes a decision, an action. And based on the action, it gets a reward. You may die, you may score and such thing, and it moves to the next screen. Okay? And inside the program, what is in there is that for each action choices, let's say they're only left and right actions. For left and right joystick moves, for each screenshot, what does left movement get? How valuable is it? So the height of the bar measures how valuable it is. So in this particular screen, if you move left, then it is this much valuable. And then there's the same set of value function for each state for the right movement. So for example, in the left movement in this screen S3, the green bar is so high, the right bar is a bit shorter. That means that, well, you should move in this S3 screen, you should move left because the bar is high. So this is sort of the idea. And when an action leads to a reward, increase the value of the screen. So initially the bar may not be correctly primed, but suppose that you're in S3 and you move left and it ends up scoring and killing a spaceship there and you move to the next screen. It was a good move, then increase this height of this bar. On the other hand, in that S3 screen, if you moved right and, well, the game ended, you died, it's a terrible move, then shorten this bar. So next time you come across this situation, you'll be making a better choice, isn't it? So this idea was implemented in 2015 by Google DeepMind. They did many different games. One of them was this Pong, and you can see here that it plays itself. The bar is okay if you have only a handful number of screenshots, but if you have like so many screens like electronic games, it's just running out of memory. It's very difficult to store each situation in a separate bar and how high the bar is for each state it is. Then it probably is easier to have a function to approximate the height of the bar in each state, isn't it? So it's a continuous state, and there's a continuous function that measures the height of the bar, okay, instead of bar, and there's so many states. It's called function approximation, and the function among the many functions, neural network happened to be one of the functions that seems to be reasonably flexible to map it. Okay? So this is called deep reinforcement learning because it uses deep neural network to approximate this value function. So typically it has a state and action as an input, goes through a neural network, and it spits out the value function. Okay? Here's an example for a very simple example. It's a game called Frozen Lake. Okay? And here, the optimal strategy is, so here is a starting point, and here's a goal, and here the F tiles are frozen, so you can step on it, you can move and keep going. While the H are holes, so if you step on it, you'll die and you lose the point. So, and the objective is start from here and at the goal. So for example, here the yellow highlighted are some safe passages. Move right, down, and then right will get you to the goal, or down, right, down, right, and get you a goal, or down, right, will get you a goal. So can you have a program that finds this passage without telling? So the reinforcement learning, again, you have a CPU, a program, and it tries to do some moves, decide a move, left, right, down, up, and then the game will get you the consequences, a reward, and the next state, and then you keep playing. And if you die, then you can restart the game again and keep playing the game many times and see where that goes, isn't it? In terms of actual computer program, conceptually, what it does is that you have a 4x4 tile. So we name these 16 tiles. So the row 1, column 1 will be here. It's array 1, put them in array. And row 4, column 4 is here, tile 16. So for that, these are the states where you are in the tile scheme. So for the 16 states, there are 4 movement choices, left, down, right, up. So, and we stored a value for each. So if you're in tile 1 and if you move left, what's the value? If you move right, what's the value? We call this Q value, this value, how valuable they are. And each time you face a particular state, let's say 4, you compare the value of this and pick the largest one and choose that action. That's how it's being guided. Okay. So again, you start at S0 and then choose an action. And then the environment will give you the next step and a reward if there is. And then you update and then move to the next tile and all this and keep going until you end the game. And you can play the game again and again. And the update rule is that the reward plus some discount like 0.9, and then the largest of the next state action among the largest. So you move to this tile. From this tile, if you have 4 actions, so if from this tile, let's say you have 4 action choices, which one gets the highest? Pick the highest value. This is the maximum possible value that you can score minus the current Q value that is stored in that particular state, in that particular action. So if there's here particular this style, for let's say here, so if you move to the next state here, what is the highest tile? That is here max Q S prime minus the current tile, and add the reward to it. Then here's a learning rate because you don't want to swing too much each step. And then, so what this says is that how you update your bar, meaning, remember, we increase or decrease the bar. The rule is to, and it's Q learning because you're updating Q, it's the old value plus a learning rate times reward plus discounted maximum Q value of the next stage minus the old value. So if this is larger than this, then there's a positive value being added. So you're increasing the Q value. If the next move is terrible, so that it's smaller than this, then this becomes a negative value and the reward being small. If so, then this will decrease and replace it with a smaller value. So this is sort of in general how it works. In the next episode, we'll see how to do this, but here's an advanced look. So for example, here, this is after running 10,000 times this frozen lake simulation. And for example, in stage 5, so here you are here, okay? And here the bars are 1, 2, 3, 4, left, down, right, up. And you can see that the sky blue bar here, down, actually has the highest value. So we move here. It's a correct move. Also, you notice that the green bar here, which is the third one, right, moving right gets you to the hole. It's a terrible move. So you can see that this kind of settle down in learning the correct moves by setting the highest bar for the correct action. So this is a quick review of an introduction to the reinforcement learning. Next episode, we'll see how to implement reinforcement learning. Thank you for watching this episode.